Okay, this is lecture number 1. You should have the slides. Actually, the website for this, if you want to see how it looks, if you haven't been to it yet, you can always find the link to the website on my main website right here. And in our website, the materials for the class, syllabus here, lecture slides, and R syntax, the R syntax file itself. And I've just taken that R syntax file and put it up on the R notebook site so that I could try to teach everything from the iPad. Hopefully this is going to record me then. IDAS notebooks, yep. So let's get into lecture. And we'll start with a couple topics. Homework 2, 4, and 6 will have your own homework data. That's number 1. And I'll give you these later on, but basically these homeworks are largely measurement focused, so measurement model focused, factor analysis, item response theory. If you don't have data, I'm happy to help facilitate getting you a data set. Hopefully one that would make sense for your program of study. But all that takes is an email to me. But I have a few specs. If you're looking at your data thinking, what do I want to do here? The idea is you're in a survey, research, or measurement context. So you really would love to see if you have like survey items or questions on an educational exam, or there's at least 6 items thought to measure 1 latent trait, or at least 8 items thought to measure 2. The numbers there are based on how often we see small numbers of items trying to measure things. The idea being the smaller number of items, the harder it is to have precise measurement of a construct that you're not observing directly. I've done that about 4 times since I started talking, so don't worry about it. If you remember, please don't hesitate to ask. Yeah. Of course. In fact, it's even better that way. Yeah, because what Lisa's experience in teaching this, she does a lot more projects than I have. I've tended to teach in more of the specialized students, like the EMS students in my life, and she's taught the folks who haven't been. And the ones that she haven't been have all their labs data usually, or have a lot of them have, not everybody has their labs data. Not every lab collects data like this, but when you've seen that, it's almost a yearly, or every time she teaches this, the shock of, but this was the gold standard in my field. Are you saying it's not good? Yes, it happens. So it's even better if you have it that way. You can have any response format, meaning Likert type items, correct, incorrect, slider bars, response time. Almost anything can really work for this. I don't really have a sample size requirement. More is always better in some cases, but it doesn't have to be. We can make things work with smaller samples. And preferably, this is data that you care about and you'd like to do something with anyway. So if it's along the lines of what you're studying, that would be fantastic. But if not, that's fine too. It's 3 homeworks and then you present what you've done. So it's not a big investment, relatively speaking, compared to a research study or a dissertation or a master's. And then there are, Lisa, this is a slide Lisa had. She'd linked to places that have data sets available that you can find as well too. All right, so my job is to answer your questions. I like this slide. She had this slide. I thought I was going to steal it. So I want to answer your questions in email, individual meetings, Zoom office hours. My office hours, unlike her, I put you in a waiting room and I talk one-on-one with you, unless you want to be in a group with other people. So and if not, if you want to wait, you can sit there in a breakout room. So it's not really group-based Zoom. I'll take that off. And you don't need to work on your homework during office hours, but you could. You can also email me, but you can also follow up with the TAs as well. Your job, ask questions. I really cannot tell you this enough. I respect your right to learn. No question is too minor or small. No question is too big. If it doesn't fit entirely in the scope of class, I will just say, hey, let's talk about it after class. But I want to let you know that I really want to have the conversation with you. I encourage it. And it's really difficult. I understand. If you were like me in grad school, you don't want to raise your hand and say, hey, I don't want to out myself in front of everybody as not knowing this. I don't know how to break down that barrier for you, but I know when I was there, it really did impede my lecture. So I just tell you that whatever you ask, I will treat it with respect and encourage. And if this still doesn't work, if you still feel shy about that for good reason, please email me or find a time to chat with me over office hours or whatever. I'll keep it confidential and nobody has to know, but I hopefully answer your question. Okay. Review the class material. There's a lot of vocabulary. I feel like statistics is like one of the worst languages to learn, right? When it comes to it, like it's one of my hobbies. I love trying to learn languages. I'm evidently really bad at it. I have this. I know I'm in my 40s clearly, and I know brain science says it gets harder and harder as you get older. And I'm like, yeah, I'll show brain science, and pretty much suck. What's that? Yeah. It's harder and harder, but I keep trying. And the same thing goes with statistics. It is another language. It's like you're immersed in a way of thinking and describing the world to really, really inelegant and really hard words, right? And then also the homework. Please don't wait until the last minute to start. Do email me if you get stuck, and if you do email me about code-related issues, it'd be great if you had either your code or your screenshot of what the error is so I can help track it down. But we're not going to have those problems because we got this, right? Yeah. Yeah, well, it's happening. In the process of learning, it's tough, right? Especially if you make a small coding error that impedes your process of learning everything else. I mean, yeah, I've been there. So yeah, that's my job. What I try to tell my students that I work with is work with it 15, 30 minutes so that you get a better conception of the problem, but don't spend 6 hours trying to track it down. If you haven't solved it or gotten help to solve it from our friends at ChatGPT, or I don't think we use Copilot, but who knows? Reach out to me. I'm happy to answer, right? I actually do the required readings. I'll do that here. REQ. Sorry for my handwriting. The required readings, at least, they give you the words that other people use. I have my own language, and as I mentioned, structural equation modeling is such a big field. There's lots of different ways of saying the same thing, and then practice on the software as well. I'll show examples in M+, but this should be really flipped. R and Lavon, the Lavon package is really what I'm going to do. And how you know Lavon is okay is that I understand in the field, the rumor has it, that the person and people who created M+, the mutanes, really don't like the person who created Lavon. So I'm like, well, if that's the case, there's something good with Lavon, right? But M+, I will say if you're used to using M+, you can use M+ and R with this M+ automation package, but you have to have M+ and R installed on the machine you're using it on. In this case, it'd be, I guess, the remote desktop. There is a STATA SEM or GSEM package, and then SAS, Calis, and Amos. There's also a proc factor. Yes. No, you can use whichever. In this class, it probably won't make a difference. Once we have the class site, it pulls directly from GitHub. So all the class files on GitHub are already part of it. But I put the request in on Monday, unfortunately. So we'll see. Hopefully it comes. One thing I really will say that is a good thing about our campus is the people who run the notebook site and the people who run the high performance computing system are great. They're just busy. So especially at this time of year, it's my fault for not submitting it earlier. All right. Other questions? All right, moving on. Today, we're going to do an introduction overview of the class, review of some of the prerequisites, and then sort of try to lay the foundation for what is a structural equation modeling and why should we use a structural equation model and why we should use it. There may be a little bit of R in RStudio in here too. I assume you probably know a little bit of it, but that's okay if you don't. I can try to help you with it. So the key questions are, what is structural equation modeling? How do structural equation models differ from linear models? Linear models meaning linear regression, analysis of variance, et cetera. What other models or methods are structural equation models related to, and why use SEM apart from your advisor telling you, hey, use an SEM, right? So today's data set, to really motivate this, we're going to make use of an example simulated data set. And if you actually go to the syntax, you will notice that not only the simulated data set, it actually is created directly in R. So you'll have to see the simulation code if you like as well. So we're pretending that this is a happiness scale. So we have 150 participants who gave us 5 items about their happiness. Back when I started grad school, a professor named Ed Diener was at University of Illinois, where I went to school. He was there was like a Time magazine with him being the happiness guy. He had the subjective well-being scale, or what he had worked on at the time. So that's where that comes from. It's like happiness, my first semester of grad school, not usually associated, highly related, right? It's tough. But what we're going to do is look at happiness and a person's marital status. You know where this is going? Uh-oh. Take nothing about this about my own marital status. This is basically participants responded one survey to one survey. It was a 5-item happiness survey. Each item used roughly a 5-item Likert scale. And I say roughly because if you look at the data, there's decimal points. That's because I generated the data under the model itself. So if that doesn't sit well with you, that's why we have generalized models, right? This is using the non-generalized version. And then are you married? Yes or no, right? Now, don't know why I put this together. I put this together like in 2015. So I don't know if that was a bad year or a good year for marriage, but anyway. But the researchers were looking at the effects of marital status and happiness. And I will hit this disclaimer right now. Take nothing from this survey other than I needed numbers to make an example. The end. All right. This is not me and my belief about whether marriage shall make you happy or unhappy. And I'm going to leave the result for later. Okay. Okay. This is just numbers and trying to make an example that's not just math. I typically use CSV files to save the data. I'm going through this. This is sort of the intro to R and other things. So if you're not an R user or a CSV user or data user, this is sort of on that part of it. So even though I simulated the data in R, you'll see there's a line of code in my R script that will output it to a CSV in the directory where the file is. And then another line right below it reads it in. And that there is to show you, if you have a CSV file, how to read it in to R as well too. The variables are not integers. I'm going to talk about that later on. And a little bit more on the import, export in R as we go in this lecture itself. That CSV file is nice. It's plain text. So in some ways, it's wonderful. Now, where it stops being wonderful, if you are in a situation where you use a character set that doesn't really fall under the ASCII code. You could have weird characters, not weird, really normal characters in many languages, just not ASCII, show up. So you got an E with an accent mark over it. Good luck with that, right? That type of thing. So that's where plain text doesn't do well for a lot of what we do anymore. But I guess you can read it with an encoding if you need to. In this file, which I have over here, you'll see, each row represents one person's observation of all their data. And each variable is separated by commas in the data set as well. And let's see here. I prefer these commented, the CSV, because if you use Windows or even on a Mac, actually Mac defaults to Sheets or whatever it is. But you can change it in settings. But if you're on Windows, it'll open up in Microsoft Excel as a CSV file. So this is the actual file itself. What comes out of R, they're just text. If you open it up in a text editor, I opened this in TextPad in Windows years ago. You get your marital status indicator 0. It means not married. 1 means married. And then each of the variable scores after that. Right. So you have to pretend that these are Likert things. Like a 10 means, yes, I strongly endorse that. So, but that opens up to be this file in Excel. How are we doing so far? Yes. You mean, oh, on your, yeah, if you want to, you can, but I think what we'll have in the future, once I get that IDAS site running, it should all just be there online, hopefully. And then the import should just be the first line of the file. So either way, you're welcome to, but it should be there once I get notification that it's up and running. I apologize for not having that right now. Okay, so there's data. Let's get into the general linear model, which I always thought was funny when I was learning statistics. The general linear model, or as we would call it, what you had to learn in 4143, the bulk of 4143, right? Which is basically, I have data, somewhat continuous. I need to predict that with some type of other either continuous or discrete data. And how do I do that? How do I make it work? Turns out, general, so back in the old days, this is even before me, I know, right? But believe it, there was time before me, and people used to teach. They used in class tests too, but anyway, not helping my cause. It would be regression on one side, analysis of variance on the other. And somewhere in the 1960s, 1970s, clearly people knew sort of the relationship between the two, but they sort of merged the two separate classes and put them into one because they share so many similarities, almost entirely, right? So that's what general linear model is, sort of takes the place of regression and analysis of variance method-wise in terms of model-wise. So the general linear model incorporates many different labels of analyses. So this is the language part under one umbrella. So if you have one outcome, one Y, and you have discrete or categorical X's, marital status being one of them, right? We would usually call that analysis of variance, right? We want to go and see if there's a difference between the married group and the non-married group on this question, for instance. If you have a continuous X, maybe your Y is happiness and X is number of days you were ill this year or something along those lines, right? That would be a continuous. We would put that into a linear regression or maybe even nonlinear regression. And if you have both continuous and categorical, we would sometimes call that analysis of covariance, right? Where you'd have something that was continuous, something that was categorical. Heaven forbid you ended up with a, oops, I don't want to do that. You ended up with a, that's not going to work either. Heaven forbid you interacted the categorical and the continuous variable, because again, in the old days, we used to say ANCOVA had the assumption that there was no interaction between the two. But that's just, yet in the general linear model, it's no big deal. We can just add that as an effect. Turns out, if you have more than one observation, in this case, a multivariate Y, that right there, this thing right here, multivariate Y, that is the case where if you have categorical X's, if you took a classical multivariate statistics class, you might have heard of multivariate analysis of variance, right? In this case, discrete predictors, continuous outcomes, more than one. If you had continuous X's, you'd have multivariate regression. Come on, iPad. Right there. We didn't really do a whole lot of that. That's a precursor to path analysis, though. Actually, all these are precursors. And then if you have them both, you might have my favorite name, Mancova. Mancova, right? And if you drive to Omaha in western Iowa, there is a town named Avoca. And I always want it to be Ancova. Have you seen that before? Anyway, on I-80, somewhere between Des Moines and Omaha. All right, so the typical assumption in each of these analyses is that your error, in this case, your residual variance for predicting either one Y or multiple errors for multiple Ys, that error follows a normal distribution. How far you are off from your prediction, tally that up across all the sample, it should be normally distributed. What that really means is that the data themselves are not necessarily normally distributed. It means they're conditionally normal distributed, meaning once you condition on the values of the predictors, there's a normal distribution around that predicted value. Right? So why I say that is you may have heard people in your life say, check to see if your outcome is normal. If it's not, transform it. No, that's not needed, right? Because what we assume in this model is conditional normality. Also, if you don't have continuous outcomes, right? If you don't have continuous y's or continuous x's, then this would fall under something called a generalized linear model, right? And that's the generalized class that you would have taken after 4140 or 6240, 60, whatever it is. That one, intermediate, that one. Too many numbers in my life right now. All right, so why we call this conditionally normal, you can tell I was heavily inspired by Lisa. These are actually my slides, but I was inspired by her on this one. Is that the model itself, like if we have an outcome here, y, and it's being predicted by a series of regression coefficients, beta 0 is an intercept, a slope multiplying x, a slope multiplying z, and the two-way interaction between x and z, all those terms right there that are not error, turn out that gives you your predicted value. And that predicted value is the mean of what you expect the person's value to be. So you don't know it for certain that's going to be their mean, but the model itself is sort of forming a distribution around that value to see how certain you are, right? And so error then, Lisa likes to call it the model for the variance. It is not really a model. It sort of just saturates the variance itself when we have one outcome, one error, one residual, one error term itself. So E, this term, is how far off your prediction is from your observation, but we characterize the sample and how far off we are with this residual variance right there. And that's where the term model for the variance comes in. When you put all this together, what we're saying about y is y itself. This model would describe a person's outcome as having a mean that's everything in the orange box, having a variance that's sigma squared error, and following a normal distribution. So literally these components are showing up on either side, either placeholder in a normal distribution. Because a normal distribution has two parameters, a mean and a variance, we put them together. I'll make one other note. What does it mean for the word model? I'll put it in quotes, right? A model shows up in the mean because all of these terms describe what its mean is. Basically, we're saying we're going to estimate its mean, but it's a function of x and z and their interaction. Right? Same thing with the variance. The variance itself here doesn't look like a model. It's saturated, right? But you could think of it as being basically, if we could make a model for it, it would just be one parameter. It would just be the sigma squared. And that parameter would have a constraint to it, right? Beta 0, beta 1, beta 2, beta 3, unconstrained. It can be any value. Sigma squared has to be positive, right? Okay, how are we doing? All right, so we can build a linear model predicting a person's happiness, right? So we're going to use the total score of that 5-item happiness scale. And by total score, I mean we have 5 items, each with a numeric value attached. We sum them together. How many of you have done that before with Likert data? No. Okay. Average out of number of items, right? Okay. So basically, you've just divided by a total by a constant. So that's right. That's right. So some function of the sum of the score. There we go. And that's why maybe I should just call it sum score more frequently. But we're going to have this be the dependent variable, right? And what we're going to do is predict that happiness with our predictor of marital status. And in this case, marital status is not a quantitative variable, so we're going to have to put numbers into it to make it a model. So here, we'll give a person a 1 if they're married and a 0 if they're not married. It's sometimes called reference coded, or you can call it dummy coding, depending on who you talk to. I think the polite term is reference. I don't know if dummy coding refers to the codee or the coder. The coded, I should say. But something is dummy about it. That could be it too. That sounds good. Let's just go with that. Let's just go with that. Let's not make this an intelligence test. All right. This is this is not it. But think of it this way. I mean, it's arbitrary to put a 0 or 1. But the reason why we will call this reference coding is when we do this, the intercept retains very special meaning. It is the mean of the reference group. So the group of zeros, the intercept represents that group mean. And then all the other effects, all the other parameters are in reference to that mean. So it'd be a group difference. So reference coding is a much more accurate way and polite way of describing it. But you will hear me, I don't know why it was beaten into me in the 1990s that I needed to call it dummy coding. And it's just become, I'm doing my best to change my language, but just so old, I guess, be lucky if I make it through the semester. All right. No, just kidding. I hope that's not the case. Oh my goodness, my tech is going crazy. All right. Next. So our beginning model is one of an empty model. Lisa loves doing this. I actually think this is really nice for didactic reasons. So basically, we're just going to take happiness and put it in a model without predicting it. And we're going to do that because we'd like to go and quantify how much variation there might be in happiness. And then once we plug in the marital status, we're going to see how much that variation is left over, sort of residual variance or R squared. So and to do this, this is where I will flip over to IDAS. That font is quite small. And of course, nothing is working to. That would be great. Yes, no problem. Please do. There we go. Is that better? Wow. Service. That's awesome. See, I wouldn't even know. And I was here. I practiced. I came in. People looked at me funny through the window. I was like, yes, I'm trying to make sure my tech works. And of course, it's not working. All right. So we have our data. Where I'm going to run this analysis, though, is this is the empty model. There we go. Okay. Yep, that is it. The empty model itself. So I'm running this model using the Lavon package in R. If you used R in intermediate, you would have used the LM function. The LM function in R is this primitive, they literally call it a primitive function. Primitive and dummy, that's what we get with this, but never mind. The LM function uses least squares to estimate linear regression. There's nothing wrong with least squares, works just fine. In fact, Lavon, though, uses something called maximum likelihood. The estimation process is a bit different. And we'll go into why they're different later on in the semester. Maximum likelihood and least squares are identical when you have a simple linear regression. So the results we have here should be the same when it comes to the fixed effects or the parts that describe the coefficients. Where they differ, though, is in residual variance. In least squares, the residual variance is unbiased, an unbiased estimate. So if you think of this empty model, the residual variance would be what you would calculate by hand. Remember the variance formula, the sum of x minus x squared, sum of x minus x bar squared over n minus 1. Maximum likelihood divides it by n. It's slightly different between the two for that. But Lavon's syntax works like this. We create a text object. So this right here is just a character string. And in there, we do things with the variable names. So what this syntax is telling you, and we're going to learn this as we go through, so I'm not going to dwell on it now. Next week, we're going to dive heavy into it. But this is effectively saying, my happiness sum score, I want to estimate its residual variance. And then Lavon fills in the other parameters to it. But I'll have a more descriptive version of this next week. So when you do that, you run this SEM function in Lavon. And again, I will describe all this to you. And you can see your result. Maybe. course. Yes. So Lisa and I debate the use of live statistics in class. And this is why, because I'm sitting here to try to make my screen, the font get bigger, and it's not. And now I can't see what's happening. All right, let's see here. What is your problem? It needs it to be a data frame, of course. All right. This is what I got for commenting my code. There we go. There it is. So when you run Lavon and you output the Lavon information, you get a bunch of numbers, right? All of this other stuff. And you're like, I had no idea I could do all of that with linear regression, right? You never saw a likelihood or an AIC or BIC before. We'll get into what all those mean. You don't know anything why there's NAs or what even this stuff happens to be. But then you get down to the bottom and you see things that are a little bit more familiar. One being the intercept and one being the variance. Right? The intercept here represents the average happiness score, sum score of 14. That's the overall average because we're not conditioning it on any status of marriage. And what's left over, this is the residual variance, so 6.702, is how much is left over, or better yet, just the sample variance itself, right? Now, again, it's the biased estimate. So sometimes we call this the population. In introstat, there was the population versus the sample. This would be the population from introstat, if you thought of it that way. And here, just to show you, come on, how this would work. Of course, give me just 1 second. But see, this is the thing. I can't leave well enough alone when it comes to R. I want to show you how this works, like with LM. This would be your LM call for it right there. And if I put summary around it, this is your least squares estimate. So again, what you see in least squares is your point estimate of your intercept of 14.73. And you'll see that's really close to what our point estimate is here. The difference in what we have is our residual 6.702. It won't even highlight. Now it won't type. Seriously, there it is. In this case, it would be our point estimate was 2.592, and this one was 2.598. Right, so it turns out we're just a slight bit smaller. What that implies, why I'm saying all this, is the difference between least squares and maximum likelihood. We are going to use maximum likelihood for almost everything in this class. So I say almost is when we add categorical variables in. It's not full information maximum likelihood we use a different variant of it. This value in maximum likelihood, the difference in our residual standard error is why the standard error of our point estimate was a little bit different too. So right here it's 0.2121, and up here it is 0.211. So it's still not that much different, but that's that. So that's Lavon. Let's see if what I have. Oh, my numbers were different. Oh, I know why. I took off my random number seed. That's why. Well, I don't need that here anymore. I had a random number seed, and why my numbers are different. Anyway, so that's a different analysis I ran. If you run it with a different random number seed, you'll get it as well. Because there are no predictors, I just described what each of these things happens to be. It's not exactly. So our once again, our intercept 8.81 in this version of the example is identical to what the mean is, 8.81. And the variance is not quite identical, but that's because the variance function in R is like least squares, divides by n minus 1, whereas in maximum likelihood, it would be like saying it divides by n. The other thing about maximum likelihood that you don't often see in least squares is that we also can get a standard error of the variance. Is it really? You can sign in. That's fantastic. That must have been earlier today. Wonderful. Not linked in the syllabus. It'll be on, if you go to the IDAS website, it should be in the teaching section. There'll be one of the classes listed there. And I realize, Eric, I didn't add you to the notebook, but I'll add you there. All right. So why I'm saying this is one of the benefits of maximum likelihood. I used to teach this class, and I dive into maximum likelihood because that was a big difference between what we did before. One of the benefits is it's really easy to calculate, relatively easy to calculate a standard error of all the parameters. So in this case, the variance has a standard error. Ever seen the standard error of the variance before? Probably not, right? Maximum likelihood, there's a reason for that, but I don't know. We'll cover that exactly. I just described all this. I guess this is it. Variability is a central concept in stats. Covariance is also important in what we do, though. So the variance themselves, this is the two formulas for variance I mentioned before. The n-1 is probably what you calculated if you had to ever calculate things by hand or with a calculator or Excel or something like that. Why that is the case is statistically it's unbiased, meaning in the long run, repeated samples, et cetera, we would have the sample estimate equal to the true value. Whereas when we use n for finite n, for n that's a relatively normal size, we're going to be a little off, right? That how far off we are as n goes to infinity shrinks, right? But it is a difference between the two. So it's ML, maximum likelihood, does this. Now, ironically, the methods that we do in structural equation modeling and factor analysis, when I say maximum likelihood, turns out if you're in, Lisa's teaching clustered multi-level this year, right? Michael's in the class. Erica, you're TA, no, I don't know, TA, yep. In that class, we could actually do a lot of those methods here as a factor analysis because multi-level and structural equation modeling share a lot of features. They use methods in multi-level or mixed models that recognize this and give variance estimates that are unbiased. And those methods you may have heard of before, they're called residual maximum likelihood or restricted maximum likelihood. Unfortunately, in structural equation modeling, I don't know of a piece of software that uses a residual likelihood function anywhere. So we just have this. Yes. Oh, it exists, but yeah, just no one's written it. Yeah. Oh, yeah. If you got software that does it. Yep. Also true. Yep. The same thing goes. So again, maximum likelihood. I teach another course, Bayesian psychometric models. A lot of people like that. Bayes, the likelihoods we use this as well. I did a study where we actually coded the residual maximum likelihood, and we could put it in Bayes. You could do that yourself as well too, but hardly anybody goes to the effort to do that. I think the reason for that is most of the time is that the sample size, quote unquote, requirements. Now, there's no such thing as a sample size requirement statistically, right? But the conventions for use with sample sizes are such that the n's are large enough to where it's a negligible or thought to be a negligible difference. Whether it is or not, we're just going to let that one fly. How are we doing? Okay, we have 2 minutes, Silberg. All right, so variance itself, and just this is the recap of getting back into statistics, right? Refreshing our memory. Variance in the standard deviation itself, quantify variation, spread. It's a concept that's not just for data, though, right? And that is statistical parameter estimates also have variance. What we can think about for variance, when you think about, I have my data, and I can look at a distribution of how far they spread, and the variance is quantifies how far, right, along the number line. Parameters work the same way. If we have an estimate of the intercept and we see their variance or standard error to it, that standard error of the intercept says how certain we are the intercept is in that range as well too. So if you were to draw a confidence interval around the intercept, you would see variance being a part of that, right? So parameters themselves have variance. And where you probably saw this first is when, I remember, again, going back in time machine here, way too long ago, the sample mean you do that to measure central tendency. And then maybe the next week you talk about measures of spread. And then eventually you put it together and you say, wait a minute, the standard error of the mean, right? That standard error of the mean talks about how consistent the mean happens to be based on the data you have. Turns out it is just the standard deviation over the square root of n. But that is the idea of the sampling distribution, that how, if we were to do this same process over and over again, how much would the mean itself change from iteration to iteration, sample to sample. So standard error is another name for standard deviation. I'm going to finish this slide, then I'll be break time. Error itself often refers, in this case, to parameters, and deviation refers to data, right? So standard error goes to parameters, deviation goes to data, right? But more generally, I want you to think about variance. When we hear variance, what it means just means how far off we are in our prediction, how much error there is. If we just have a sample of data, you don't really think it's error, it just quantifies it, but error relative to the mean, right? If the mean is your only prediction function. All right, I'm going to stop here. Let's take 10 minutes, and hopefully there will be voice on my recording when I come back. And I will talk to you in just a bit. Yes? No, probably not. I'd be surprised if we did here. I may be wrong about that, but I don't think so. Thank you. Okay. So that Levon variance estimate 3.35, we could always convert that back to unbiased as well too. Right there. Yeah, same. Okay. So now let's go and predict happiness with the marital status indicator, shall we? Okay. So now what we have here is married, the 0-1 variable. Right? So in this case, the reference group is people who are not married. So the intercept represents their average score, which is actually an intercept of 8.41, right? And then the slope, that's what this right here, where it says regressions, happens to be. 0.744 represents the difference in happiness for married people versus non-married people, right? So probably seen that before. This looks like non-married people score slightly happier, slightly. Wait, there's a story in this. Wait till the end, though. Wait till the end. Is it an artifact? Is it not? Now you might think one thing right now, but I'm giving away. I'm like showing all the secrets. I've got no secrets. Anyway, p-value 0.014. Yes, we're not doing Bayes, so I've got to go back into frequentist land to describe this. Wherever your type 1 error rate, I don't know, is 0.14 bigger than it or less than it, right? So if you use a 0.05 for alpha, you would say this is a significant effect, right? And then our variance estimate is 3.39 in the slide example, not on the IDAS example. Previously, it was 3.55, actually, no, 3.53, right? So it has come down just a bit because that variance is being explained. Basically, variance in our happiness sum score is explained by a person's marital status. How we do it? Yeah. That's right. Yeah, that's right. And not the n-1 versus n. It's Levon's empty model versus Levon's model with the predictor. And actually, if we were to go and look at that predictor in Levon, nope. This is why I don't usually teach from the iPad, unfortunately. I love the iPad. It's just not capable here. The model itself looks like this. This would look like the syntax in R if you use the LM function. Happiness score tilde married. Those are both names of variables in the data set. So Levon's syntax is really, really close to R when it comes to linear model type things. And it turns out most of what we do in path analysis are linear model type things. So Levon's syntax will let you specify like a lot of regressions all at once in a similar way that if you've used R, it should look a little familiar to you. Yes. Yes. And so we'll talk a little bit more about this as we go along. Levon, I struggle between telling you everything and telling you the shortcut. No, this is good. This is actually, yes, a covariance. And it's trying to estimate the covariance of a variable on one side with the variable on the other. And in this case, a variable covaries with itself. What we call a variable covarying with itself is just its variance.
Yes.
But yes, the double tilde is a way to enact estimates of covariances. The single tilde is regression coefficients, or the mean. And then there's a couple other ones. There's a tilde equal, and that is defining a latent variable with a series of observed variables. Yes, and there are other ones to define variables as well. So Levon is setting up a way to do a bunch of linear model type things all at once in a system that is hopefully fairly shorthand, quick for syntax. Thank you for the question. All right, I just interpreted these values already. So if you wanted to flip these around, if you wanted to make the reference group what it would be, instead of saying non-married people are the reference group, we call it married people. Well, the mean for married people, that predicted value is from our original model where the reference was non-married, our original intercept plus our original coefficient for married, that's 9.215, that's their mean. So what would be the intercept? If we reversed it, the intercept would be 9.215, and the slope would be negative 0.744, right? So basically the idea being, you may hear this in other places, and it's fine, you can do this. A lot of times people will say, oh, you don't get all the means out of a model when you code it with the dummy codes. Yes, but all of the means are functions of the model parameters. One way to solve that is to recode and rerun the analysis. That usually is okay until you get into weird interaction variables and random effects and so forth. A better way is to literally figure out what these are and go backwards to get the mean, right? So you can get the mean of each. And the other part of it is you can say, oh, I know the mean's 9.215. What's its variance? Well, we could calculate that too. And actually, Levon will let you create, I'm not going to show this today, but as we get in class, you can create a variable that is the sum of these two coefficients. Then it shows up in output, and it gets a standard error with it as well too. So in M+, it's called the new command. In Levon, it's just an added variable that you can go and define. So sometimes you may want to find that as well too. And that's one of the other nice things about doing things this way. Now we can do a hypothesis test for the parameters. Again, this is the recap, all of your intro. We want to see whether or not beta 0 is not equal to 0. The null hypothesis would be that, I'm sorry, beta 1, that's our regression coefficient representing the difference in marital happiness between married and non-married. We want to test the hypothesis at 0. We'd set up a hypothesis test that looked like this. In your previous classes, you may find the result in analysis of variance tables, right? And you might find an F test. This is another difference between the structural equation modeling landscape, or better yet, maximum likelihood, and sums of squares. In maximum likelihood, we don't have sums of squares. Sums of squares is what we do to estimate a lot of these models, or least squares, right? And those kind of fall out. Maximum likelihood, we use something called the likelihood function, which I probably will try to spare you the details of mostly. But we can still get at hypothesis tests based on some of the beautiful things that maximum likelihood gives us. And I say beautiful in the sense that, like, mathematically, it's really cool, right? So for instance, if you look at this output right here and you want to test this hypothesis, you would look at this Z value right here and this P value, right? The Z value comes from taking our estimate and dividing by the standard error. In maximum likelihood, we call this a Wald test, named after, I think, Abraham Wald, famous statistician, 1940s. If you ever look up, there's a famous picture of a World War II bomber or jet with a bunch of holes in it, and talking about, like, they wanted to reinforce where the holes were, and he's like, no, if the hole, anyway, he was involved in that. That's the Wald guy. This is a hypothesis test in maximum likelihood for any parameter, because it turns out in maximum likelihood, as n goes to infinity, the distribution of the parameter converges with certainty to a normal distribution. The mean of that normal distribution is the value of the parameter, and the variance, or the standard deviation of it, is right here. So if you wanted to test your parameter you could leverage that fact, create a z-score out of it, and determine whether or not that z-score is significantly different from 0. Right? That is enabled by maximum likelihood. Here in Lisa's multi-level class, you might see this z-score get converted to a t-test. And that t-test involves a few other assumptions about how we go and calculate this itself. So the z-score, again, its assumption is a very large n. But for not so large n, you might see a t there that still is like a walled test, but that's what we talk about as well too. So that's yet another difference. We don't have an overall ANOVA table, but what we can do in maximum likelihood is there's basically 3 different ways of testing hypotheses about parameters. One is the walled test. The walled test involves fitting a model that has the parameter in it. Right? Another is model comparison. Right? We fit a model before with no predictor. We had a model with a predictor. Right? The model with the predictor subsumes the intercept from the model before. So basically they're nested, right? We could use something called a likelihood ratio test, where we take -2 times the difference in log likelihood of the models. That's hypothesis test strategy number 2. That gets used when you have sets of parameters. Maybe you put in 15 predictors and you want to say, is any one of these significant? Easy way to do that, relatively speaking. There is also a multivariate walled test. We won't get into that in this class. The third way is the most interesting of all. It's called the score test. The score test is where you can estimate a model without the parameter. So they go back to our empty model right here and say, hey, what would have the parameter been if I had included it? It's like a magic trick. Yeah, I didn't put the marital status in, but had I put it in, would it have been significant? That's what score tests provide. You don't see score tests as much, except as we go into class, there are parts of model building in structural equation modeling that rely upon them. Sometimes they're called Lagrangian multipliers tests. Sometimes they're called, oh my goodness, I'm blanking on their term now. Oh my goodness. I just wrote a paper on this. Anyway, it'll come to me, but we'll see it again. So why I'm trying to say this is, if this is your first time doing anything with maximum likelihood, there are some differences in how you see the results, but the same hypothesis building continues. And in fact, maximum likelihood is such an important feature, particularly in multivariate models, when we have more than one variable in it, as in almost everything we do going forward in this class, because it provides much better missing data protection, right? Missing data in maximum likelihood, we can not have to throw out an entire person if they only give us some of the observations in the model. What that provides is an assumption, meets an assumption usually called missing at random, which is better than what we would get with least squares. So maximum likelihood is often looked at as a gold standard estimator. I'd say maximum likelihood is certainly, Bayesian relies on maximum likelihood's likelihood function. So both of those are involved too. So for most statistical methods that you get into that have more than one outcome, you're going to be using a form of maximum likelihood for the most part. Unless you're using something from the 1960s when that wasn't really well developed. Okay, so if we interpret the residual variance, the other way to look at that is with the empty model estimate, we have our predicted model estimate. We can get an R squared. So this tells you the impact or the amount of variance, proportion of variance explained by marital status of happiness is 3.9% or 0.039. Is that a big effect? I don't think so. Marital status explains 4% of happiness. Now, I told you not to read anything to the result, all right? Still not there yet, but let me just talk about one other thing. You may have seen standardized coefficients before. You may not have, depending on who taught you linear models or where you got that information. Standardized coefficients are ways that we try to compare. So if we have, and where it's not as important when we have a single outcome. Here we're just predicting happiness, right? Or sorry, predicting happiness, right? With one outcome. But what if we had happiness and we had another variable like, I don't know, perceived place in the world. I don't know. Pick another important variable to predicting with marital happiness. You may want to say which effect is stronger, right? The problem with that is saying, is happiness, does marital status impact happiness more, or does it impact this other outcome more, right? It's hard to quantify that because that other outcome may have a different scale, a different metric. So what we want to do, just like we would take a correlation coefficient describes how two variables are related linearly without units involved. It's a standardized covariance, if you will. We can standardize our regression coefficients. In this case, instead of saying what we have now, which is in our current explanation, beta 1 represents the change in y for a 1 unit change of married. Well, in our case, 1 unit change of married means going from 0 to 1, so that's why we call it a difference, right? But 1 unit is on the metric, beta 1 is on the metrics of units of y per units of x. Unit in this case being like the raw equivalent of y, the raw value of y. Instead of that, what we can also talk about, standardized coefficients describe things in standard deviations. So how many standard deviations of y changes per standard deviation of x? Now, in the example I'm giving you here with the discrete outcome, standard deviation of x is a weird number, right? A standardized unit. There's only 2 groups. What's the standardized value there? So there are different versions of standardized coefficients. I'm only putting this here, and I'm going to go into the depth of this. I'm actually not even going to talk a whole lot about this yet. But as we go into output, both M plus and Levon will quickly give you standardized coefficients for some of the parameters that we have. And the reason for that is when we have more than one outcome, which is almost every single of the models that we're going to get into in here, we may need to compare values of some of our coefficients in a relative sense across other outcomes. Right? Whether it's prediction of actual variables, whether it's predicting observed variables with a latent variable. Usually that's the case that shows up. The standardized coefficient shows up a lot in what we do. And this is just putting it in your mind. We're going to talk more about those as we get forward, actually next week, how that works. But here, we can actually get the standardized solution here. And you'll see that the standardized value is 0.17, meaning some score goes up 0.97 standard deviations. And depending on the type, yes, this is literally trying to say per standard deviation increase in marital status, which is a weird thing to think about, happiness goes up 0.197 standard deviations. Yes. Mm-hmm. Yes. Yeah, the random number seed, yeah, the numbers are different. They should, if you go in this context, it should be the same. But somehow I changed the seed, or I deleted the seed from the file when I was editing it for here. So sorry about that. All right, so that was your review of linear models. How are we doing so far? Saw most of it before? Maybe not Levon, but certainly the linear models, right? Let's get into measurement. You may or may not have taken a measurement class, and that's okay if you haven't. But I'm going to give you a quick primer on constructs, reliability, and general linear models. The general linear model, regression ANOVA, assumed that all variables were measured without error. However, in most of what we do in the social sciences involving surveys or questionnaires or tests, those values that we have are imprecise. So think of it this way. In our previous example, Y, the happiness sum score, was trying to represent or characterize a person's overall happiness by adding up their scores on a bunch of variables that were supposed to measure it, right? But it was not perfectly reliable. Meaning, if we were to basically take a person, have them fill out the survey, wipe their mind clean, like they never saw it before. That's right. And then give them another survey. That's right. Yep. I think Men in Black's, the person who made that movie with the little like whatever that thing was a psychometrician, like trained somewhere. Yeah, that's exactly right. We were to wipe them clean, basically wipe their mind clean, or take a different time of their life, wipe their mind clean. We would see that happiness score might change, right? That's what we talk about with reliability, meaning the score itself is not the variable, even though it looks like we've observed it. It's a proxy for an overall variable that we cannot observe. And when that's the case, we have to put a model together with it. And there's problems in that. There's measurement error. There may be model misspecification. There's a whole bunch of error itself. So actually, it turns out adding up the scores is this, I call it a very naive statistical model. All the scores have measurement error. So related to measurement of an error in a test score is the reliability of a test, right? And the reliability, if we have no error whatsoever, reliability should be 1. It's an index between 0 and 1, right? So we want high reliability because that gives us confidence that our measurement is precise. The lower the reliability, the less precision we have in our instrument, right? So the bigger the difference this person score might be if we gave them this test multiple times. All right. So in our example so far, the happiness variable is the sum of a 5-item happiness score. So there's this thing called test theory. It was like my first class I took in grad school, and yes, I'm still talking about it now. It was awesome. It is a latent trait is test theory is sort of what underlies latent trait theory. You may hear it in different terms. The word test theory, where I came to it, was a professor named Roderick McDonald at Illinois. He had a book on the topic called Test Theory to Unified Treatment. You're going to read chapters from it a few weeks from now, a couple chapters of it. It's a general collection of statistics, or better yet, you can think of this theory of psychological tests and measurement, or psychometric theory. Psychometric theory is used even when we're not in psychology. Right? That's the thought. Basically, how do we measure phenomenon that characterize an individual when we can't directly observe it? Test theory is a collection of statistical models that we use to develop and evaluate instruments, so measurement instruments, surveys, tests, etc. We operationalize practical problems. It provides answers to these problems. And measurement models are statistical models. And there are 3 branches that we like to talk about. There's classical test theory. I'm going to quickly go through this. Add things together. What's that? Yes. That's right. I'm going to do this on your assignments. So clearly it has a place in the world. But classical test theory is sort of quantifying what we know about a score, how much error we have in a score, and other characteristics of a score when we add the values of items together. We're going to see this in this class as a restrictive, or as a model. Not a lot of people do. And in fact, there's debate over whether we should or not. I'm clearly in camp model on this one, all right? It's not only a model, it's a super restrictive model that we would never believe that would ever fit our data, or would seldom fit our data. But it was the first thing that came along. A latent trait is this unobservable construct or factor. And this is the interesting thing about this class, by the way. We started with linear models, and we dive into, reliability, measurement, and all that stuff. We're putting the 2 together. That's what the SEM starts to do. So before it sounded very separate from now, but it turns out you're going to see they're all integrated into a similar framework as we go forward. So a latent trait we have to talk about because that's a huge part of the measurement model itself. Why would you have it? It's an unobservable construct, psychological construct. I guess it doesn't even have to be psychological. For instance, I may or may not be a consultant for one of the Major League Baseball teams, and there is a model about that I've helped them put together that's psychometric. That's pretty fun as well too. And we wouldn't call that a psychological construct. I cannot. I'm not allowed to say. Not allowed to say. But it's a lot of fun. And whomever, if you're listening, thanks. Thanks for letting me. Let's really play with the data. I don't know if this is being recorded. I don't even know if it's going to make the internet. But if it does, that's all I want to say about it. But the point I'm trying to make is the latent variable, the construct itself, doesn't have to be psychological. It can fit into a lot of different contexts, right? So here, actually, I guess I probably would say it's about a decision-making process. Anyway, you may have heard of, like, we talked about marital happiness or extroversion or introversion, intelligence, all that. Ability, right? Big one. Anything we're doing in educational measurement. If you have a test you took in school, that's a construct, right? The ISASP that we give students, score that comes back in math, that's supposed to represent their mathematics ability at a given grade level, something along those lines, right? All of those, same things. So how do we measure something that's unobservable is the big question. That always perplexes me, right? And the answer is we have a model by which we say, if this were true, we should see this and work backwards to try to figure out what the thing is. The big picture is that we take items, sometimes called indicators in the structural equation model world, observed variables, and we say that those are the things that measure this unobservable quantity, right? So latent traits can be measured with observed responses to questions or items of a survey. A new latent variable is created from the common variance across the indicators. So you think it this way. If you had 5 items like we have here, and they all had roughly the same correlation, right? Maybe they all were correlated 0.7 or 0.8, something along those lines. That's like a common amount of variation. Something's common to all of them. We take that idea and we turn it into the latent variable itself. It's a very that's a very rough way of describing how things function. The flip of that is if you have a bunch of variables that are uncorrelated, zero correlation, which is really hard to do, mind you, particularly when you're talking about human beings, right? We have highly correlated things that come from all of us. If you do, you likely don't have a latent variable there, right? So the flip it. So you got to have things that measure it, that are observable, that are related, and that relationship is indicating this thing underlying, right? Do you remember in basic stat, if we said there was a correlation between X and Y, there were like 3 different reasons why that may be the case? Remember this? Everybody talked about that correlate? This is sort of correlation versus causation. One was X causes Y. That's supposed to be an arrow, right? One was Y causes X. Remember the last one? You ever talked about this? There might be some Z that causes X and causes Y. That's us in the measurement construct right here. Right here. We didn't observe happiness, but had we observed happiness, we would have a good sense of knowing why a person responded on question 1 this way and a question 2 that way. Yeah. Right. That's exactly right. That's exactly right. That's right. So what I'm saying here is coming about that idea from different perspectives. One being, there's this thing called intelligence, and if we could observe it directly, we'd know how people would do, right? But we can't, so we have to go figure out how they would do and then go infer what their intelligence might be based on it. All right. So there's a bit of differences here. The 3 different areas, I didn't put those in, are classical test theory, which we're not really talking a whole lot, confirmatory factor analysis, and then the binary item response version of confirmatory factor analysis, which is the latter 2. And these all have weird names to what the thing we're measuring is. In classical test theory, the sum of the items is supposed to be a reflection or an estimate of a person's what we call true score, right, if we could observe it. In factor analysis, we call that the factor score. Sometimes we call it F. In item response theory, we substitute that idea with a Greek character theta, and theta is still the same thing, right? If it's intelligence, it's still intelligence, it's just a different symbol. If we do item response theory in education, sometimes we call that ability. And then there's this other field of item response theory like data that stemmed not in education, but in psychology, another branching of the literature of this, called item factor analysis, that approached binary data, but with more of the factor analytic terms. Sometimes we still call that a factor score. So there's all these different words for the same ideas as you go through. And we're going to get into this as we go, and in the interest of time, I'm just going to flip through here. Structural equation modeling is what we do when we form our constructs, right? What I did in the previous example is I took the 5 items, I summed them together. That was my estimate of a person's happiness. There's problems with that methodologically, right? It's not perfectly reliable. What we're going to do is build a model for happiness and then predict it in that model. We predict it in that model, that is structural equation models, a structural equation model itself. And we're going to get there in just a bit. So structural equation modeling is, I'd say, path analysis with latent variables. Path analysis is a bunch of variables predicting, some being external or exogenous, some being internal, but a series of interrelated variables. This gets into, if you've taken a causal inference class, you may have heard of directed acyclic graph. That's been around way longer than causal inference, graph theory, Bayesian networks. All these are similar features, similar things. And then, all right, skip the history lesson. You can read that if you want. So 5 happiness items are now the focal point. That was our sum from before. I don't need to do that. Oftentimes we use indices to, reliability indices to sort of describe how much precision we've measured things with. You've probably heard of coefficient alpha, right? Cronbach, 1954, Psychometrica, like the most cited Psychometrica article. Psychometrica is a journal known for heavily technical quantitative methods, psychometrics. Doesn't get a lot of citations. Its impact factor is like 2. It's not big. Maybe it's bigger than that now, but ironically, if everybody cited their methods, it would be off the charts because the methods that showed up, maximum likelihood factor analysis showed up there. Structural equation modeling showed up there. If you cite your methods, that thing would be off the chart. But nobody reads it because it's you have to be highly trained in very technical nuance to get there, right? Not just that, it's hard. But anyway, coefficient alpha came from Psychometrica. It's an index of reliability. It is not necessarily what we need. And we're going to learn about reliability, how we quantify it, and how it relates to different entities. Reliability for what? Well, coefficient alpha is reliability for a sum score under certain assumptions. But as you know, we may end up not having sum scores. Anyway, I'm going to skip this because I really want to get to the motivating part. And we come back to this in confirmatory factor analysis. But what is confirmatory factor analysis? This measurement model. We have to figure out which items measure the same construct. Well, that's usually where you write scales in the first place, right? The satisfaction with life scale that I was telling you about before, I think one of them is, what questions is, conditions of my life are close to ideal, right? Or when I think about the past, I've been more happy than sad, something like that, right? Something that would indicate happiness. The CFA itself is a linear model that predicts each of those observed variables as if we had observed the factor score from the first place, right? It's like saying item 1, item 2, item 3, item 4, item 5. Each one of them has a separate regression line being predicted by the score of this thing that we never observed. It's like I did regression, but I forgot to observe X. You may be thinking, how do I do that? Well, it turns out mathematically, you can. If you have enough observed variables, you can show that mathematically, yeah, if that score were to be there, we could figure out what its coefficients happen to be. And it seemed to fit. So it's not exploratory factor analysis. In confirmatory factor analysis, we know we prescribe this item measures this latent variable, right? In exploratory factor analysis, the first thing we ask are, how many latent variables, how many factors do I have? And then which ones measure what? What do they mean? We skip all that because we design it. We build this into our research program. The uses of confirmatory factor analysis models, we use this to analyze relationships or provide differences, provide scores for people as well too. And honestly, each item's model looks like this, a linear regression. We have different symbols. Mu is the intercept. We call that an item intercept. Should have been beta 0, it's mu. Lambda is a slope, beta 1. Well, we call this a factor loading. F is the actual factor if we had observed the score of a person. So what it means is, if we knew what a person's happiness was, and we knew how well this item related to it, we could predict how well what they would have said on that item, right? And then we flip that around to go and get a factor score. Okay, history, some more history. Item response theory is that with categorical data. I put way too much in this lecture. But we're going to teach this from this unified view of test theory standpoint here. So yes, there is a course on item response theory being offered in spring in educational measurement and statistics. It's going to be specifically item response theory. This class, and that's a good thing for some reasons. It's also, it's a deep dive into it. This class says, oh, item response theory is but one of many measurement models, right? You may not even hear that word measurement model said in the item response theory class, and that's normal. That is just the world it happens to sit in. Okay. All right, let's motivate why we're doing this. This is really what I wanted to get to. What happens? Hey, if your variables are not 100% reliable, what's the big deal, right? Right? We know we can't use it. We're not supposed to use a linear model if X or Y have some error to it, but yeah, what's the matter? There are several things that could be bad that could happen. Your effects may be biased, right? Meaning, depending on the type of variable, beta 1 may say there's a relationship and there really isn't, right? Your standard errors may be biased. That's bad when it comes to hypothesis tests, particularly if you think you have more precision than your data really suggest. So that's really bad. So basically, any conclusions you make can be drawn into question when your variables aren't 100% reliable. But that happens all the time. I mean, we do this. My name is Jonathan, and I've put in sum scores in linear models before. It's just sum scores anonymous or something like that, right? It's just how it works. The answer, though, is not aggregate. Don't sum things up. Structural equation modeling is the methodology that tries to address this, right? It tries you can use structural equation modeling to see the relationship between latent constructs. So maybe we have multiple measures of happiness. How do they relate together? We could see how it use it to talk about how latent and observed constructs come together, right? How does marital status factor into the model? It can also give you more complex relationships, like mediational models or other ways that you can go and look at values. So basically, anything that you could do in a linear regression is now part of that structural equation modeling umbrella. It's a generalization of linear modeling using observed and latent variables. And sometimes those latent variables get called random effects. And it also overlaps highly with multi-level models. You can think of this example. I have 5 items nested within a person. So we have 5 responses nested within a single observation. So like a multi-level model too. Okay, so we often use something called a path diagram or a directed acyclic graph to describe relationships. So here, this is marital status. This is happiness. This is a directed arc, a directed arrow, saying that marital status predicts happiness. So when you see one arrow at the end, and this is all the way, next week's lecture, we're talking about this, right? Well, there's also some leftover variation here, right? These are standardized units, so 0.2. So when this goes up by 1 standard deviation, happiness goes up by 0.2 standard deviation. And what's left over is, we explained roughly 4% of the variance. This is what's left over. The double-sided arrow is one way of notating how much error is in each of the variables you see there. In structural equation modeling, this is a little bit what we want to get to. We don't need the sum score. So this bottom part that you see right here is a path diagram depicting a confirmatory factor analysis model where happiness is the latent variable, the circle. These are the 5 observed questions that we asked the person. And each one of these arrows connecting the latent variable to the observed represents the factor loading or the slope. Again, these are standardized coefficients. So that means for every 1 standard deviation increase in happiness, we'd expect the variable to go up by this amount of standard deviations each. And this is what is left over in terms of proportion of variance not explained in the standardized solution. So in this model, we can build a happiness latent variable right here. We didn't observe this, but we can still estimate everything else. What structural equation modeling will do, again, this confirmatory factor analysis, if all we have this is probably what we call it, a CFA model. But in structural equation modeling, we're like, wait a minute, I want to predict happiness with my marital status. Now, I'm assuming marital status is perfectly measured, 100% reliable. It may not be. Let's imagine that everybody responding was truthful. Let's put it that way. Because that's one way that you would have a lack of reliability, right? How's that sound? Otherwise, yes, but I generated these data, so I know it is, right? Let's just put it from the abstract here. These are simulated data right there. But happiness is not. So what we do is we build this structural equation model that includes this prediction relationship, where happiness is now an outcome in this sense, but a predictor in this. Or another way of putting it, if you want to get really into the weeds here, if you look at the combined effect here, marital status affects happiness potentially, and happiness affects your score on a variable. If we look at these two paths, we'd say happiness actually mediates the relationship between marital status and how you scored on a variable as well too. And all this happens in this framework called structural equation modeling. And not only that, we don't output happiness. We can get all of that without even having a score for people. We have the latent variable taking the place of the score in the analysis. Now, I remember when I was in your shoes, I was like, how the heck do you do that? Right? Because I've done a bunch of regressions before and all of them had X and Y observed. That's the magic of SEM, or that's just math? That's math. I'd be happy to describe that to you. So there we go. So yeah, so this part right here, we would often call the measurement model, right? Where we form the latent variable. And this part we would call the structural model. When we put them together, it's a structural equation model. So it turns out this whole thing, I'm sorry, did you want to see that again? Yeah, okay, cool. I'll take after what I'm about to do and all the mistakes I'll make, I'll take a positive comment. Maybe I wasn't positive, I'll take it that way. Sorry, I didn't want to get carried away with like happiness here. But if you were to think about what this model is implying, it's 6 different regressions all at once, right? Each one of these, 1, 2, 3, 4, 5, there are 5 outcomes. They're all predicted by happiness, right? Intercept, slope, residual, right? And then happiness is being predicted by marital status, right? And again, that's a dummy-coded variable. So we could just put all this into one analysis and get the results. So I did this. And this is why, again, SEM is often called path analysis with latent variables. We're going to not have this part next week. And we'll see many things. If we didn't have this, bottom line right here, and happiness was observed, this would be called like a multivariate regression. But we'll get to that next week. Okay. So now, in Levon, I estimated this model. And this was the coefficient, the standardized coefficient. I'm using standardized coefficients here because I'm sort of comparing across models with outcomes with different scales, right? So in the original model where I took the sum score, we saw the standardized coefficient was 0.197. So 1 standard deviation increase per 1 standard deviation of married, p-value 0.014. Do all this in the latent variable, standardized coefficient 0.272, so we underestimated it, p-value 0.243. So yeah, I told you, wait, man, thought one thing about me, but I'm like, marital status does not have an impact on happiness. This right here, that is no, take no inference from me on this. Happiness and marriage, like anything in life, anything, if you're like me, anything can affect your happiness positively and negatively. And this is not a reflection on the person I'm married to at all. So let's not take it that way. This was to go and take something that was like somewhat alarming and be like, if you look at the data this way, I'm like, get married, be happy. I mean, it's like a 4% explanation of variance. And now I'm like, wait a minute. Anybody who followed that advice needed to learn structural equation model, right? So there's the punchline. They would be, but it's not. We're not sure in this sample whether that's significant or not. But think about what's happening behind the scenes, because this is the main thing. When you have a variable that doesn't have perfect reliability, but you treat it as if it does, think of it that way, right? Perfect reliability means zero measurement error. Okay, not perfect reliability means there's some measurement error, some value there. So when you say no, this is perfectly reliable, let's sum score, perfectly reliable, the first analysis, you think you have less error than you actually do. And that's a big problem when it comes to analysis, right? The standard error of our coefficient in our previous analysis was 0.08. It's 0.233 when we treat it as a latent variable, right? And when we go and see that, when we say, wait a minute, we have this problem, this demonstrates what it affects, right? The z-score here is estimate divided by standard error. Now, this estimate is actually higher. And this is actually a part of the thing you may have learned about in a previous class. Spearman talked about this over 120 years ago. Attenuated correlations. Ever heard that before? The Spearman correction formula. If you took a correlation between variables without perfect reliability, Spearman came up with a formula to sort of correct it. Basically, the correlation between unreliable variables will be an underestimate. Well, a regression slope is a correlation that's been rescaled, right? So yes, we got a higher relationship, but the error is much higher. And that's what you end up seeing in a lot of studies with latent variables that don't treat them as such. We think we have more precision in our data than we really do. And there was a 10, 15 years ago, the beginning of the replication crisis in social science. You've heard this before? There's it started with the idea that I remember there was some study of some number of studies where people tried to replicate results and some ridiculously small percentage verified, like 30% or something like that. And this led rise to this replicability crisis in psychology and other places. What was seldom talked about in that debate, but again, I'm the psychometrician in the corner over here looking at it. I'm like, yeah, if you're treating your constructs as if they're perfectly reliable and they're not, right? There's already a chance this could be a non-zero relationship, but there's much more of a chance here, right? Already chance this is a zero relationship, excuse me. So structural equation modeling, motivating what it does is pure beginning before it decided to grow so large and just like the big tech companies buy up all the smaller companies around it, subsume all the methods around it. Structural equation modeling is started with this idea. How do we build models for variables that are not perfectly reliable? Yes. Yeah, absolutely. Actually, it goes a couple of things. The CFA is a step in a validation process in a way. So yeah, even if it's been validated before, validation is never really complete. I mean, sort of talk about it in a lot of the intro classes, like, well, this is shown to be valid, but it depends on samples. It depends on use cases. It depends on a lot of things. But this is a version of validation right here. Yeah, so the Cronbach alpha assumes it tells you reliability for adding up these variables if each of these loadings were equal. That's what it does. But it's adding up the variables that you're making a score out of. More importantly, if we're doing this construct, we're predicting something latent. If we want to talk about the latent score, we need reliability for it. But that's kind of coming along. Okay, So this is where we're headed. Let me, there we go. Wrapping up. Yeah, I'm going to wrap up. So we have 1 minute left. Okay. So next week, the reading assessment chapter 2 of Capital. Remember, hard chapter. Don't just let it dissuade you. I'm not going to ask you questions about matrices. You don't need matrix algebra to be in this class. Read the words. Take a look at the questions on the quiz. Those are the things to focus on. Now, if you're into matrices, cool. I'm guessing you're probably not, because I know there's not a lot of people who love matrices like I love matrices. But I remember this when I teach, and I'll keep you. This will be, try to get through it. Questions you have, let me know. The assignment should be up on Icon already. Be prepared. Next week, I'm going to give out a homework. It's going to be due a week later on path analysis with data that I'm giving you. So it'll reinforce that. So you don't need your data yet for that. Okay? All right. Anything else? I got less than a minute. And it's 3:20. Thank you. Good to see you. Whatever problems I had with the audio today, I will resolve next week. I'll bring a Mac and we'll call it good. Okay? Thanks, everybody.